this is where we left off, or where we'll start. Computational complexity. Before, when we were analyzing algorithms, we analyze the algorithms in terms of like some input size n, right? Like if we're doing a linear search over a list of n things, right? And we're concerned with how much work is being done relative to n and how the amount of work changes as n changes, okay? Now, when looking at iterative factorial, and I ask you, if we go all the way up here, if I ask you, what's the computational complexity of iterative factorial, take a second, look at it, and what do you say? Like, what would you say it is? This isn't a trick question. N. How many times does that loop run? Often when you're looking at your iterative implementations of things, you look to the loops as your quick and dirty way to know. N. Why? Well, I starts at 1 and it goes all the way to n inclusively, so whatever. And you'll notice that the plus plus I is now I plus plus. So, it's n. But when you look at the recursive one, that little trick of looking directly to the loops doesn't really work anymore. But it's the same ultimate idea. Because when you looked at the loop, it wasn't so much looking at the loop, it was how many times is this chunk of code going to run? And to do that, you looked here at the loop. But really the question we were answering was how many times is this code getting run? How many times will this code get run? Let's say n was 100. How many times is that code going to run? It's not a trick question. What do you think?
100.
100. Why do you say that?
Because it's going to go through each number from 100 to 0.
Yeah. Because n will be 100, then it'll be 99, then it'll be 98, then it'll be 97, all of that to 1 to 0. And it stops. This code is going to get executed n times because n is starting at 100, and every time it runs, it decreases that n by 1 for each subsequent call. If n was 1,000, it would be 1,000. If it was 1,000,000,000, it would be 1,000,000,000. It's linear. So you might think, oh, I can't do the trick of looking at the loops. Well, yes, but it's not about the loops. It's how many times that code is going to get run. And it's the same thing here. How many times is this code going to get run? When analyzed recursive, the idea is the same. How many operations will we need relative to the size of n? How much amount of work done scales as n changes? When looking at recursive factorial, there are constant time operations. There's a recursive call, which means the code inside the function will run repeatedly. The question is how many times will that method get called? Function, whatever you want to call it. In this case, it's a static method. How many times will it get called? Well, this, right? For some arbitrary n, it'll be run for n, and then n minus 1, and then n minus 2, all the way down to 0. So that's a total of n plus 1 times, but we don't care about that plus 1. It's linear. So ultimately, it's the same trick. How many times is this code going to get run? So this is also a linear time function. In fact, both the iterative and the recursive are operating very similar. Like the algorithm, you can look at the code, and one's iterative, one's recursive, and you can look at the code and you clearly can see the differences. But the idea of the algorithm is really the same. There's really no core difference in the underlying algorithm. Has anyone heard of the Fibonacci sequence? 1.5, 2, 3, a couple people, great. Fibonacci sequence is defined recursively. You might not think of it recursively, but it is. I mean, we can generate the Fibonacci sequence pretty easily. For those of you that don't know what it is, this is what it is. And if you're wondering, how do you generate it? Well, you start with the numbers 0 and 1. And then to generate the next number, you sum the previous two numbers. So if I have 0 and 1, what's 0 plus 1? Who said 2? 0 plus 1 is 1. Oh, great. So the third Fibonacci number is 1. And then I have the two previous numbers are now 1 and 1. 1 that we just generated and the 1 from before. So the next one is 2. So then it's 2 plus 1, which is 3. Then it's 3 plus 2, which is 5. And then it's 5 plus 3, which is 8. And so on, and so on, and so on. So we generate it like that. Oh, I was going to get you to figure it out, but that's the hint right there. So to generate the sequence, you start with 0 and 1. Then to get the subsequent number, you add the preceding two together. So here is some iterative code. I'm going to give you a minute. Look at this code, make it make sense in your head about what it's doing. It's not recursive, it's iterative. I have P for previous, I have C for current, and then I have next for the next number. When I start this, I start it with previous at 0, current at 1, and next is set to 0, but it's because I don't really care what it is. These are the two starting numbers. Then the loop goes, where I put in some arbitrary n. Assume n is some large value. How is this going to work? Well, it goes by going, well, next is current plus previous. So that's 1. Right? Then what do? Previous equals current. Okay, so the 0 disappears. Put the 1 there from current. And then current, well, we replace current what's in next, which happens to be the same value. And we start again. Next equals current plus previous. 1 and 1. Well, that's now 2. Current goes into previous. Next goes into current. Repeat. 1 plus 2. 3. Move current down. Move next down. Repeat. All right, 2 plus 3, 5. Move the 3 down, move the 5 down, and I'm certain, if you didn't have it figured out already, this pattern made it pretty clear. This is an iterative Fibonacci number generator. It's nice. What's the computational complexity of this code? Take a moment, look at it, and come up with an answer. There's no trick here. There's nothing you don't know.
It's also be n?
Pardon?
It's also be n?
Why?
It looks like it's only doing, well, it's doing a fixed number of operations per each time. And it only goes over n number of times depending on how many, well, depending on whatever n is, right?
Yeah. I mean, we could say n-ish, because I starts at 2, and we got this less than or equal to thing. But it's close enough to n that, yeah, it's linear. As n grows, the amount of work I need to do grows linearly. If I double the size of n, I just have to run the algorithm twice as long. So this is a nice iterative function. But if we go and look at the actual recursive definition of Fibonacci numbers, so this is like a mathematical formulation of the Fibonacci numbers. To generate any arbitrary Fibonacci number n, if n is 0, the answer is 0. If n is 1, the answer is 1. if n is greater than 1, then it's the sum of the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. So, if that's not clear, pick any value right here. Let's say 377. I don't know what the n is there. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15. Is 15 0? No. Is 15 1? No. So it's that third case, that recursive case, which means take the Fibonacci of 14 and add it to the Fibonacci of 13. Well, that's 233 plus 144. That gives you 377. That's what that means. So initially we generated it from the bottom up, but we could generate any arbitrary one by looking at the previous two, assuming they exist. And if they don't, well, we can go calculate them, and so on and so on and so on. Now this particular idea has, I mean, you could think of it as having two base cases. When n is 0 is a base case and when n is 1 is a base case. But in my implementation here, I just combine them into like an if with an or. If n is 0 or 1, return n, because I guess I was counting the first Fibonacci number at 1. Maybe I should have been counting it at 0. Oops. Whatever. So, because if it's 0, it's 0. If it's 1, it's 1. If it's 2, well, we calculate it by fib of 1 plus fib of 0. So far, so good? Look at this recursive code. Look at the recursive formulation, and then look at the iterative. Again, isn't this recursive formulation just, there's something about it. It's so clean. It's so clear. Now, there is some nuance here. So there's the base case. You can kind of think of it as two base cases, fine. But what's interesting is each time, listen very carefully to the question, each time for some arbitrarily large n, so assume it's not 0 or 1. If I call recursive Fibonacci on some arbitrarily large n, how many calls to recursive Fibonacci does that one call, that first call, make?
N minus 1.
Nope. How many, let me put it, maybe I should rephrase the question. I call recursive Fibonacci with n is like 1,000,000, let's say. Right? So I call it once myself, where n is 1,000,000. Recursive Fibonacci 1,000,000. And then recursive Fibonacci makes recursive calls, right? But how many calls does that recursive Fibonacci of 1,000,000 make?
Then you kind of go down like a tree almost.
Well, yeah, but how many calls does it make?
2 million?
Not 2,000,000, no, just you're working way too hard. Listen to the question as it is. Don't try to skip at anything, connect any dots that don't exist. I call recursive Fibonacci. Recursive Fibonacci, that one call frame. How many calls to recursive Fibonacci does it make?
N squared?
N squared? No, you're working way too hard. You're thinking computational complexity. I'm not talking about computational complexity yet. I'm talking about how many calls to recursive Fibonacci does recursive Fibonacci make?
That almost makes 2.
What?
2.
2. What were you going to say?
I was gonna say
2. Why? There's no trick question. Why? Because there's literally 2. There's one there and one there. In order to know recursive Fibonacci, to know what the Fibonacci number is for some arbitrary n, I need to know what n minus 1 is and n minus 2 is. And then once I know those, I add the result together to give you back. Yeah.
Like if you end up calling like, say 1,000,000 times, won't it like turn into like a tree and like just you'll have like almost like, I don't know how to really explain it, but you go in, it'll call that one and that one calls 2 more and then that one calls 2 more.
Okay.
And it'll also call 2 more and then 2 more and then 2
Yeah, so if I put n at 1,000,000, I call it at 1,000,000. How many calls does that make? 2. And each of those calls how many? 2. So now we have 4. And each of those calls how many? So now we have 8. And each of those calls how many? So now we have 16. And each of those calls how many? 32, 64, 128, 256, 512, and so on and so on and so on and so on and so on. Huh. Now, when I asked you about, when we were talking about the computational complexity of factorial, the rule was how many times does that chunk of code get called? When n is some arbitrary number, that code was called for n, n minus 1, n minus 2, and so on and so on and so on. This is a little different because we have 2 calls. So the question is, so from some arbitrarily large n, how many times is this going to get called? So with recursive factorial, if the input n was n, that function would get called n times, right? For n, n minus 1, n minus 2, and so on. Here, if I call recursive Fibonacci on some arbitrarily large n, how many times is this chunk of code going to get run?
2 to the power of n?
2 to the power of n is absolutely correct. So, if we go look at the iterative, this was linear. We agreed this was linear. You said it was linear. We all agreed it was linear. Why is it linear? That loop runs like n times. So that chunk of code runs n times. If I double the input size, I double the total amount of work. Okay? If my input size is 1,000,000, I have to do like 1,000,000 units of work. With the recursive Fibonacci, if n is 1,000,000, I have to do roughly 2 to the power of n work. What is 2 to the power of 1,000,000? Can someone tell me real quick?
Big.
What'd you say?
Big.
Big? I think you're right. Did I say 1,000,000 or 1,000,000,000? You know what? It doesn't matter. Pick one. What's 2 to the 1,000,000? Is someone really not calculating that right? Go to Google, type 2 to the power of 1,000,000.
I don't even think you can say that number.
Yeah.
Times 10 to the what?
3,000, let's say 301030. I'm just gonna say that. It's 10 to the power of that.
2
10 to the power of.
to the power of 1,000,000. 1, 2,
1,000,
3, 0.
It's pretty much 10 to the power of 300.
Google won't even tell you.
Literally, it just says 19 times 10. Literally, it says 19.9315685 times 10 to the power of, I don't even know. It won't tell you.
Fine, let's do 2 to the power of 1,000 and maybe Google will tell us. There. With the iterative implementation, it was linear. If the input size was 1,000, it would have to do like 1,000 units of work. With the recursive implementation, if my input size was 1,000, it would have to do 1.071509 times 10 to the 301. That's 301 zeros after a 1. Okay? That's, which is worse? Probably the one that's 2 to the power of it, that's exponential, yeah. It's not because it's recursive that it's exponential. It's the underlying algorithm. Exponential is bad. Bad, 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 bad. You do not want to be working with algorithms that are exponential. Sometimes you've got no other choice. Clearly in this scenario, we do, because we were able to implement Fibonacci in linear time. If I were to use that code If I were to use that code, the recursive Fibonacci code, to calculate the 1000th Fibonacci number, my computer wouldn't do it. It'll stop. It'll give up. No, it won't give up. I'm going to give up and tell it to stop. It's going to take way too long. For the sake of argument, let's do it. Just to show you what I mean. So I'm going to wait for IntelliJ to load. Hopefully I actually did load it. Let's run both to give you a sense of how it's doing. Now, of course, while doing this whole difference here begs the question, well, why was the recursive one worse? Why was it 2 to the n where the other one was linear? What made the recursive one so bad? We'll talk about that. Perfect. So that's the iterative and then recursive. Let's do 100, because why not? No, let's start with something like 10. Okay? IntelliJ's indexing, so I can't even run it. Maybe if I do this, maybe it will. All right, well, I'm letting IntelliJ index. We'll carry on a little. Okay, let's talk about why it's so bad. In the iterative one, how many times, look at this iterative code, right? It generates every number up to the one you want, right? If I want the 100th, it'll generate 0. I mean, it kind of starts with 0 and 1. But it'll generate the 2nd, 3rd, 4th, 5th, 6th, and so on, all the way up to 100. How many times does it calculate the 99th Fibonacci number? Just once. It only needs to calculate it once. Think of this, right? How many times did it get to 5 plus 3? 8. We only had to calculate that 8 once, right? Each of the Fibonacci numbers only had to get calculated once. But we have exactly what you said. We have this like branching thing going on. Like just like you said. We've got this tree. If I call fib 6, I need to have a call for fib 5 and fib 4. Because we need to know fib 6 minus 1 and 6 minus 2 and add the results together. And fib 5 needs to know fib 4 and fib 3, and fib 4 needs to know fib 3 and fib 2. And fib 4 needs 3 and 2, and fib 3 needs 2 and 1, and fib 3 needs 2 and 1, and fib 2 needs 1 and 0. And fib 3 needs 2 and 1, and fib 2 needs... We got a problem here, though. For example, just with such a small number 6, how many times am I calculating the 3rd Fibonacci number? Three. How many times are we calculating the 2nd Fibonacci number? 1, 2, 3, 4, 5, right? I'm calculating each individual Fibonacci number multiple times. Every time I calculate fib 6, for example, fib n, I need to calculate fib n minus 1 and n minus 2, right? And then fib n minus 1 needs to calculate fib n minus 1 minus 1, which is always going to be the same thing over here. And look, fib 6 only really needs to calculate the 4th Fibonacci number once, but it's doing it twice here, and it's going to do it twice. Every time Because when you calculate n minus the n minus 1th Fibonacci number and the n minus 2 Fibonacci number, when calculating the n minus 1th, n minus 1 Fibonacci number and n minus 1 minus 2 Fibonacci number, the n minus 1 minus 1 is the same thing as n minus 2. And both of those trees, this is only with fib 6. Both of those trees are going to be huge. Imagine 10. I need to calculate fib 8 twice. And fib 8 needs to calculate fib 7 4 times. Oh my God, we're in big trouble here. That's where all this extra work is coming. I'm recalculating all of the Fibonacci numbers several times. And that's terrible. And you probably don't get a sense of the scale with fib 6. But to give you a sense of the scale, let's look at how the code works. What were you going to say?
Could you also use a
Yeah, you can do bookkeeping, of course. Yeah. So here's fib 10, linear. Run. Come on. Okay, it's 55. Let's do recursive with 10. Okay, with 10, I didn't really notice a difference. If you were wondering why it was taking so long, that was the compiling that took a while. Right? At the bottom you see like build. So let's make it like 50. But let's go back to iterative. Oh, I'm guessing the problem is we have an overflow. Maybe I should be using like a long or something, but let's change this to a long. Let's try that again. No, we're still, okay, the problem is the 50th Fibonacci number is probably a pretty big number. So what the value is not particularly interesting to me. It's the amount of time it took. The reality is, though, it did the calculation. The reason that it's giving us some weird number is because of an overflow issue where there's just not enough bytes to represent the data. But we can see it's running like that. Let's try recursive. Yeah, wait, you know what? Let me go back to iterative and I want to see if it's changing all these to longs. We'll fix it. Yeah, let's try that. There, much better. Perfect. And I'm going to do the same here. Long, long. There. Okay. So there. It's still running like that. The iterative one, very fast. Let's try recursive with 50. Okay, build, parsing. Okay, it's running. I'm just going to keep lecturing. Maybe we'll check. We'll keep checking on it to see if it finishes before we're done. Both are going to give you the same answer. Which one's better? Linear.
Yes.
When given a choice between two functions that perform the same task to give you, like, think of it black box, input, output, doing the exact same thing, and one is linear and one is exponential, you take the linear one. All right. So this is the whole 2 to the power of n. Now, Towers of Hanoi, I'm going to move through this fairly quickly, so I'm going to keep it very high level. But Towers of Hanoi, there's an old legend with Towers of Hanoi. Who here has heard of Towers of Hanoi? Who here has at least seen this game before? There you go. Right? So the process is this. Or sorry, this is the game. And there's an old legend that goes with it. It's this old legend where there's these I don't know, these religious monks or something. And they work in this secret underground cave in the middle of who knows where, okay? And they have 52 very precious, very holy religious plates. They're made of gold, okay? They're very thin though, so they're light. And there's 52 of them. And each plate is a little bigger than the previous. And they are stacked perfectly, like that, okay? All right. And these plates are very special. And these plates must be moved from here to there. Okay? But there's very important rules about the plates. Only one plate can be moved at a time. So these monks have to move one plate at a time. And a plate that is bigger can never be placed on top of a plate that is smaller. Never. They have to be stacked with the biggest, smaller, like that. And in the process of moving them, there's only one other spot in this super secret, special, religiously important cave that you can place the plates. And it's right here. Okay? This temporary spot. That's the 3 pegs. Okay? So the goal is you got to move all the plates from one to the other. And after the monks are done moving all 52 plates, the universe ends. Okay? Don't ask me where these are. It's a super secret place. I don't know. I don't know where the legend came from, but I believe it's really important. Okay? So what is the algorithm for moving these plates? Well, it's this process. This is the pattern you follow. And you'll notice that the pattern repeats. And with every subsequently larger disk, you just keep repeating the same pattern over and over and over to move the disks around. And it just so happens that there is a beautifully simple recursive algorithm for doing Towers of Hanoi. And it requires very little, it requires some intuition, but it's not too bad. I'm not going to write the algorithm down, but we can think of it at a high level that we have when talking about recursion. Like, for example, when I said how many people were in the row, the rule was, well, it's 1 plus however many people are after you. And remember how I was like, well, that feels like you're skipping a step. Well, yes and no, because you just get how many people after you by asking the next guy how many people are after them, including themselves as well, and so on and so on and so on. So there's all this delegation of work taking place. So the trick is to consider that when moving a disk or a golden plate, there is a source peg and a destination peg. I want to move this peg or this plate from here to some destination place. And that has to be one of the 2 posts. But with this information, okay, the destination peg and an extra peg. Further, what is considered the source and destination, an extra peg, is relative to when and what disk is being moved. So here's the idea. If I want to move all of the disks, all of the golden plates from here to there, here's what I have to do. And think recursively now. Move all disks above the last one to the middle peg. Move the last disk. And then move all the disks from the middle peg to the destination, the final peg. And then we're done, right? That's all we got to do. Now again, you're thinking, well, hold on, you skipped a step. But this is where the recursion comes in. How do we move all of these n minus 1 disks to that extra peg. You just said move all of those n minus 1 disks to that extra peg. You can't do that. Yeah, we can because we're doing it recursively. So how do we move all of these disks to where we want to put them? The destination peg for these n minus 1 disks on top is the middle peg right now. So how do I move them there? Well, very simple. All I have to do is remove the n minus 2 plates on top of the second smallest one to the final peg, move the middle peg, or that second biggest one, to the center peg, and then the n minus 2 pegs here. And then you go, well, hold on, you're skipping a step. You just said move the n minus 2 pegs to the final last one. How do you do that? Simple. You move the n minus 3 to the middle peg, and then that last one to the final one, and so on and so on and so on and so on and so on. This has 2 recursive calls in it though. Recursively move the n minus 1 plates to the middle peg, move the 1 plate, and then recursively move the n minus 1 plates from the middle peg to the destination peg. There's 2 recursive calls there. We have this 2 to the power of n relationship. How fast do you think a monk, oh wait, before we do it, oh my god, it finished. Finally. Look at that. Feb 50, we did it, yay. Now the funny thing here is if you're thinking, yeah, okay, but we know recursive is slower. But remember, I finished telling you at the beginning of the class that Java will turn that recursion into like an iterative version, really. But the problem is it's an iterative version of the algorithm that recalculates fib of n minus 2 twice. Right? When we only need to calculate it once. So it was an iterative version of the worst algorithm. It's not the recursive versus iterative. It is the underlying algorithm and how it works that was different. The iterative Fibonacci was linear. The recursive Fibonacci was exponential because it did all that extra calculations. We can have a recursive one that doesn't very easily, especially if you do just simple bookkeeping like you suggested with like a map or something. And then suddenly we can have a linear time recursive one as well. But it's the actual algorithm, not because it's recursive, but it's the algorithm that was terrible. Now, moving these plates is going to have that 2 to the power of n relationship. How quickly do you think a monk can move 1 plate? They're really experienced. They've been doing this their whole lives, so they're pretty quick at it. How fast do you think a monk can move 1 plate? You want to say like a monk can move a plate 1 a second? For the sake of, they're really good at it. So let's say 1 a second, right? So if they have 52 plates, that's 2 to the power of 52. Times 10 to the 15. Okay, so if they have to do that, that's how many like steps they have to do for each of the plates. Not for each, for all of the plates, for 52 plates, these are the number of steps they have to do. And if they're doing 1 a second, how long will it take for the universe to end? That's the question I want to answer, right? Because remember, when all those plates move, the universe ends. So times 10 to the 15, okay, divided by 60 to get the number of minutes. Divide that by 60 to get the number of hours, right? So let's see how many hours there are. Okay, times 10 to the 12. All right. So there's 24 hours in a day and 365 days in a year. So this will be how many years it takes. And it's still, that's a lot. So it'll take 142 million years. And that's not that long. But they're moving at 1 a second, so I don't know. We got like 142 million more years to go, I guess, until the universe ends because these monks are moving so well. Although they've been doing it since, maybe they've been doing it, maybe we only have like half time left. I don't know. Maybe they're halfway done. Who knows? Sorry. Any questions about recursion so far? I hope you like it, because I certainly do. I think it's fun. No questions? No nothing? All right. The next topic. Searching. For the purpose of this topic, we are going to let's define searching. Okay? Searching is a process of looking for something, a specific thing, in some collection to know if it exists or not. I know it might sound silly to define searching, you all know what it means, but just to make sure there's no confusion about what we want to do, searching. Does a number exist in an array, for example? And to write an algorithm to solve the problem, all that one needs to do is to have it say if something is there or not. That's all that's required. And it needs to be correct, of course. But given what we like to call like a needle, the thing we're looking for, and a haystack, the thing we're looking through, we want the function or method, whatever we want to call it and how we're using it, we want it to return true if it exists, false if it doesn't. I don't care how it does what it does. I just need it to work and be correct. That's searching. Any algorithm that works is sufficient. However, the focus that we're going to talk about is two very intuitive ideas on how to search for things. Two very common ones. Two that you have definitely used in your life, whether you like it or not. The first one is a linear search. Okay? Who here's ever done a linear search before? Who here's ever done a linear search not in code, but had a collection of things you needed to go through to find something? Of course you have. Of course you have. You've all done this. Who here has ever... What time we got? Does anyone have a textbook in here? Anyone have a book with you? Are you for real? Come on. Someone's got to have a textbook or something. I don't have one with me. I need one for an example. You got one? Perfect. I hope it's thick.
Well, that's a big boy.
It's a big boy?
I don't have one right now in mind.
You don't have one?
Yeah.
You've got one?
Yeah.
How big is it?
It's kind of big.
It's kind of big. I'm sure it'll do the trick. I'll give it back. Don't worry. It was still in the package. I won't tell your world religion professor. I need to find page... Hold on, I want to see how many pages are in the book. I want to find page 300. Okay, there's like 650 pages in here. I want to find page 300. Do I do this? No. 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 No, that's not it. No. We're not even on page 1 yet, for crying out loud. No, page 7, 8, 9, 10, 11.
You're getting there.
I'm getting there. Is this how you turn to page 300? Yeah, that's how you do it. No, what you do is you go, well, let's go about here. All right, I turn to page 408. Okay? All numbers less than 408 are on this side. I'm emphasizing it because you're backwards, right? All numbers bigger than 408 are on this side. Which side do I continue to look on? I'm looking for page 300. The side with the numbers less than 400. And if you're wondering why, it's because page 300 is less than 400. And if I have pages with numbers less than 400 over here, and pages that are greater than 400 over here, is there any way page 300 is over here? How many pages did I just get rid of in this search? Heck of a lot more than one. When I was doing the linear search, every time I turned a page, I eliminated one thing from my search. No. Everything I looked at, I only eliminated one thing. Here, I'm able to eliminate half-ish the things. I turn again. I'm on page 250. I now know between here and here, I have pages that are greater than 250, but less than 400, and pages less than 250 over here. Where do I continue the search? In here. Every time I make a guess, I'm eliminating, hopefully, roughly half of the things I need to look for. Or I need to look through to find the thing I'm looking for. You've all done this. But there's a reason it works that we'll talk about next time. Thank you very much.